Now, we have quite a few different uses of radioactive isotopes in science. So, one way that we use it in chemistry is to use isotopes to study the way a chemical reaction occurs. This is what we call a mechanism. We talked about this a little bit. We talked about this back in chapter 14. We can also use a tracer, and a tracer is a radioactive isotope that we use to trace the path of the atoms of an element in a biochemical reaction. So a tracer, again, this is a radioactive isotope that's used to trace the path of the atoms of an element in a, usually it's a biochemical reaction. We can use isotopes to determine the relative ages of an object, like we talked about with radioactive dating. We can use isotopes to help us determine the structure of molecules. You'll see a little bit more about that in organic chemistry. We can use tracers in medicine to help trace the flow of blood and determine possible constrictions or obstructions in the circulatory system. And it can also be used to image organs and test their functionality as well. Now, what about the biological effect of all this radiation? Well, the fundamental unit of radioactivity is called the curie. And 1 curie is equal to 3.70 times 10 to the 10th nuclear disintegrations per second. And so this number, where 1 curie is equal to this many, 3.7 times 10 to the 10th nuclear disintegrations per second, this is equivalent to 1 gram of radium. Now, 1 millicurie, this is equal to 1/1000th of a curie. Okay, so you may hear the term curie, you may hear the term millicurie. Okay, now the intensity of the radiation depends on the disintegrations, the energy, and the type of radiation. And the most common unit of radiation absorbed is called the rad, where rad stands for radiation absorbed dose, or rad, radiation absorbed dose. This is the amount of radiation that results in the absorption of 1 times 10 to the minus second joules per kilogram of irradiated material. Now, most of the time, rads are multiplied by relative biological effectiveness, or RBE factor, that's used to measure the biological damage by radiation. Okay, and that's called a REM. Okay. Now there's 3, and so what we're looking at here, this, keep in mind that this chart was about 2010 when I grabbed it. But this is going to tell you, this basically is going to be the yearly radiation dosage for Americans. So from cosmic rays, depending on where you're at, you're getting about 20 to 50 millirems per year. If air travel, if you're making like 1 flight a month, you're getting 5 millirems per year. But if you're going on multiple flights, you're getting a lot more radiation. New fallout from nuclear weapons tests, you're getting about 5 millirems a year. Nuclear waste, you're getting about 2 millirems a year. So we, in general, Americans are exposed to about 133 to 188 millirems a year. And so if you're way above that number, that is a problem. Now, like I said, there's 3 major particles that we deal with: the alpha, the beta, and the gamma that we have to deal with. Now, alpha, we know, since this is going to be the helium atom, okay, the Alpha particle, this is the heaviest particle. And it's going to do the least amount of damage. And usually alpha particles are stopped by clothes and skin. The next one, the beta particle, this gets through the upper layers of skin. Think of it as like a sunburn. Okay. But instead of that sunburn only affecting the top layer, it's going to affect several layers underneath. So think of it's like a sunburn, just deeper. Okay. Gamma rays, this has high energies. These do the most damage. And you, like I said, beta particles. If you're wearing clothes, you're fine. But if your skin is exposed, it's going to damage the first couple layers of skin. But it's going to be like a really high intense sunburn. Okay, gamma rays. These are the ones that we're really concerned with the most. Those are the ones that we're extremely concerned with the most. Now that being said, when you're getting an X-ray, the reason why we're wearing that lead shield, and the technician taking the X-ray is in another room or behind a corner, is because they're trying to limit the exposure to gamma rays. Now that being said, while I'm saying that alpha and beta particles aren't going to do as much damage as a gamma ray, if an alpha or beta emitter is ingested, they can cause major damage to tissues and organs. And so that's actually one of the concerns that people have about, about terrorists using like a dirty bomb where, you have radiated iodine and that being absorbed, because we have to eat, we have to drink water, and getting that radioactive isotope inside your body where it's going to do the most amount of damage.